All right. To begin with, the homologous series of alcohols. Alcohols are the organic molecules. They have the hydroxyl group, the OH group attached to them. But remember, before I move any further, remember the alcohols that we study, as stated exactly in IGCSE book, are not exactly alcohols, but alkanols. Why? Because we add one hydroxyl group to an alkane molecule. So alkane and ol for the suffix of alcohol, that's what we go for. So C, it's CnH2n plus 1 OH, which means the general formula of CnH2n plus 2. We substituted one hydrogen out of it, so it's not really plus 2, it's plus 1. And then we added a hydroxyl group to it, so it's OH. That's how this general formula comes into being. So this general formula is actually representing alkanols, all right? Alkanes, alcohols that are based on alkanes. So the suffix is not exactly ol, it's anol to the alkane stem. For example, CH3OH is methanol. Now, this is not only to get you introduced with what we are about to do, this is also to introduce to you how we commonly name them, or to give you a generic idea that what can they manipulate or do in exams in terms of questions. Let me give you a quick idea. Something that Cambridge has repeatedly used are enols. Now, I hope as soon as I say the name, you do understand that ene has been converted into in, which means there would be a double bond in the structure. And of course, there are ols, which means there is going to be an alcohol group or hydroxyl group in the structure. A combination of both would be known as enols. Okay, this is a repeated example. Let's say in upcoming papers, they come up with inols. What would that be? Of course, Yn represents the triple bond, and ol represents the alcohol or hydroxyl group. So a combination of both is inols. So yeah, Cambridge may come up with something new, something out of the ordinary, something they have never used in the book in a way like this. So getting familiar with this kind of stuff actually prepares you for something you haven't seen before. I hope you get the point, right?
Yes, sir.
Good, good. Now, let's move further. Let's classify alcohols. Alcohols are classified in such a way that, which is pretty much similar to the halogenoalkane. The alcoholic group is attached to the first carbon, right? That carbon, if is attached to one chain, it's a primary alcohol. That carbon, if it is attached to two chains like this, is a secondary alcohol. That carbon, if that's attached to three chains at a time, it's a tertiary alcohol. Another idea to tell the same thing, if OH is connected to a CH2, it's probably a primary alcohol. If OH is connected to a CH, it's probably a secondary alcohol. If OH is connected to a C, it's probably a tertiary alcohol. Now, if those are all alkyl chains, that's how what we are going to go for. So it can be something different than an alkyl chain. All right? But you'll still call it a secondary alcohol group. Now, the book is going to go for something even more sophisticated than that. Let's take a look. Propanol is classified as primary alcohol, propan-2-ol secondary alcohol, 2-methyl, propan-2-ol tertiary alcohol, which clearly gives us the idea that 1-ols are usually primary alcohols. Secondary and tertiary alcohol would never have 1-ol in their name. That's really not possible at all. I hope you get the idea. They always have a bigger number. It can be 2, it can be 3, it can be
Yes.
anything. Right? So even if you don't have the structure, you have just the name, keep the possibility of something being a primary or maybe a higher secondary or tertiary alcohol from its name. But before you jump to a conclusion, it's better to think about the structure in your mind and imagine it for a few seconds before we move ahead. It's always good to be safe. Moving on, there are alcohols with more than one OH group. We've studied an example in section 15.4. 15.4 was actually the last topic of hydrocarbons chapter. We were talking about alkenes, we were talking about oxidation of alkenes, and we were forming diols. Now, the very name diol itself represents two alcoholic group or OH groups. Now, this was this. Now, as soon as we have more than one OH group in the structure, every OH group can be classified as what it is. Now, both of them are primary. Why? Because the carbon atom connected to it is only connected to one carbon chain. Now, consider propane 1,2-diol, this one. If I draw the structure, it would be something like this. This is CH2, this is CH, then this is CH3. If I draw both the alcoholic groups under the structure, this would be something like it. Now, let me tell you that this is a primary alcohol and this is a secondary alcohol. That's what's mentioned over here. It can be really easy for them to put an alcohol or multiple alcohols with a structure and then convert it into an MCQ asking you whether which one is primary or how many primary or how many secondary alcohols are there in complicated structures, bigger structures such as. Now, do you understand why the first one primary and the second one secondary? The reason for it. It's just a yes or no question. You don't need to explain it.
Yes.
All right. What about you, Laba? Can we move ahead, clearing it up? Okay, great. So moving ahead, properties of alcohols. Before I move any further, do keep in mind the properties that we studied back in IGCSE, and those properties are actually a prerequisite over here. Now, let me tell you that the ones that we studied back in IGCSE was that the few starting small alcohols all have pretty sweet smell. They're all liquids, they're all soluble in water, and they don't have very high melting point, right? They are actually volatile liquids which can evaporate easily. These were all the basic properties that were given previously in the IGCSE book. The IGCSE book also had one specific sentence that they are soluble in water in all proportions. No matter which proportion you think of, 10% alcohol, 90% water, the vice versa, 90% alcohol, 10% water, 50-50, 60-40, 70-30, all of them soluble. All right. We're going to discuss both the things, their boiling points or even their miscibility over here, but in a little more detail. So starting with the very first line, alcohols have higher boiling points than expected when compared with other organic molecules with the similar MR. Even methanol, which is the smallest alcohol and it has the lowest MR, is a liquid at room temperature. Now, the reason being hydrogen bonding. Since you haven't studied hydrogen bonding back in IGCSE, so here we can teach you the reason in detail. So yeah, that's the hydrogen bonding. Because there is an O, there is an H, there is an O, there is an H over in the structure, so hydrogen bonding is possible. Alcohol molecules have hydrogen bonds among them. Alcohol molecules do have hydrogen bonds when dissolved in water. And that also explains why smaller alcohol molecules are so miscible and they dissolve so well in water. Remember the any proportion line. So this means that water molecules and alcohol molecules, especially the smaller alcohol ones, since they are more soluble in water than the bigger ones, actually try to make hydrogen bonds between one another. So these are the properties of alcohols that have been previously used in all three papers. Actually, if I say all five papers, that won't be wrong. Paper 1 to paper 5. Moving on. comparing the acidity of alcohols in water. Now, when I use the word acidity, here we are talking about dissolving in water and dissociating of the molecule and giving the proton. Now, that's the definition of an acid in the very last pages of your IGCSE book, that acid is anything that can donate a proton, right? So alcohols can donate a proton, water bond dissociation can donate a proton. This is what we have studied so far in AS. Now here we are talking about comparing the acidity, which means we're going to talk about whether an alcohol can donate a proton better or water can. We're comparing both of them. Well, let me tell you, both of them are not acids. So they're not going to donate a lot of protons, which means they're going to donate much less in terms of donation of protons, but we are still going to compare which one is a better acid or which one's good at donating protons. So once dissolved in water, ethanol molecules do not dissociate to any great extent. There is a very small degree of dissociation, so it produces a very small number of protons. How do we know that? The position of equilibrium lies well over to the left, which one means there was much more of a reverse reaction than there was a forward one. Now, this favors the undissociated molecules, which means more of the ethanol molecules exist in the molecular shape than they do in their ionic form. Now, don't forget that this is the ethoxide ion, which means we have taken the stem S and we have simply used the term oxide ion along with it, which means if I use a C2H5O negative, it's ethoxide. And if I replace the C2H5 with CH3, or maybe I replace it with C3H7, it would be methoxide or propoxide. So basically, in terms of naming, this is alkoxide ion, right? So that's how we name it. Don't forget the method because they're never always going to go for ethoxide. They may use meth or prop or but. So you should be able to come up with a name appropriately. Moving on. In case of water, water decomposes as H in OH. The concentration of H positive ions is much lower. We can say that ethanol is a weaker acid than water, which means the capability of ethanol for donating a proton is even much less than water. Then there must be a very good explanation for it, hence the whole paragraph up next. Now, if we look at this paragraph is going to discuss the charges and how good they are in donating the proton, as well as since these both are reversible reactions, we are also going to discuss how good amount of the reverse reaction is going to occur. So pay close attention to it. Now, ethanol molecules are less likely to dissociate and form H positive ion. That's the first thing. Second thing, because of the electron donating alkyl, and in this case, we have the ethyl group bonded to the negatively charged oxygen atom, which is this. In this case, we're talking about the ethoxide ion. The positive inductive effect of the ethyl group has the effect of concentrating the more negative charge. If I write it like this, H3C and CH2 and O negative, you'll understand that this has an electron donating effect, right? We call it a positive inductive effect. Now, the positive inductive effect tries to distribute the whole charge on oxygen. So the ethoxide ion more readily accepts the proton, right? So it is going to accept the proton back and be converted into its molecular shape, the reverse reaction. On the other hand, if I talk about water, water is simply H and OH. If we take out H out of it, then it would be simply just this part. Now there is no positive inductive effect. This cannot accept the proton as easily as ethoxide ion did. So we say that water is a better acid than ethanol. We can also repeat the line written in the book, ethanol is a weaker acid than water. And that's only due to the presence of the electron donating alkyl group or the positive inductive effect. That's all you have to discuss. I hope you get it. If you have any questions, throw them now.
Sir, can you discuss the ethanol thing again?
Okay, it's this inductive effect. Don't forget that when we are using this sign, we're talking about the inductive effect. When the sign is moving towards the charged species, it means what's trying to happen over here is the electron donating effect. We also call it a positive inductive effect. Now, this positive inductive effect makes it easy for this oxygen to accept a proton back, all right, and be converted from the ethoxide ion back into ethanol, which means more of the ethoxide ion. Well, first thing, it would dissociating much less than water. All right, it was already dissociating less. Now, if the more of reverse reaction would happen, I hope you understand that position of equilibrium would be well over to the left-hand side, which means there would be much more molecules of ethanol in molecular form than they are in their dissociated form. So we can safely say ethanol is a weaker acid than water. Why? One, it dissociated less. Two, because of its positive inductive effect due to the presence of an alkyl group, the ethoxide ion can easily accept a proton and be converted into the molecular form again. So there would be more molecular form as compared to the dissociated form, hence a weaker acid. Remember, the better is the acid which can dissociate more. Remember, I hope you remember from the example of HCl in CH3COOH back from my GCSE that we said, and we used the same example in the acid-base chapter in AS book as well, that this one dissociates completely. HCl can dissociate almost completely. That's why we call it a very good acid. Why? It does not like to stay in molecular form. Instead, it likes to be converted into ions. It likes to donate more and more proton, hence a better acid. On the other hand, we call ethanoic acid as a weak acid. Why? It loves to stay in the form of molecules. Only a few of them dissociate into ions and donate protons. So of course, HCl is more acidic than ethanoic acid. In our case, water would be more acidic than ethanol. So ethanol is a weaker acid than water, or you can say water has a better acidity than ethanol. And that is due to no electron donating alkyl group attached in water to have a positive inductive effect, hence a better acid. Which means keep in mind, every time you're going to have more electron donating groups attached to an ion, in that case, the acceptance of proton would just made easier. All right?
Yes,
Are
sir.
we
Yes.
good? Okay, okay. Let's move on. Now, as soon as I get to reactions to make alcohol, now remember there are some reactions that he did back in IGCSE. IGCSE had two reactions. Number one was fermentation. We're not even discussing fermentation over here. This is the first line he went with, and he never even bothered to put it as a bullet because that was something different, and that's totally a prerequisite. The second one was hydration of ethene, and that's the first reaction. And hydration of ethene is something that we have studied previously, so I don't need to go over this again. But remember that the mechanism followed was electrophilic addition, right? So it converted an alkene into an alcohol. Also, we were able to oxidize alkene with the help of strong oxidizing agents such as cold dilute acidified potassium manganate 7 to convert them into alcohols. And we formed diols in the process. Remember, these are alcohols that we formed with hydration of alkene, and with oxidation, we are able to form diols, a specific category of alcohols. So if you're supposed to form simply alcohols with one hydroxyl group, go for this reaction. If you're supposed to form with more than one hydroxyl group, you can go for this reaction. Keep this stuff in mind because this is going to allow you to make a better mind map. Moving on. In our previous chapter, chapter number 16, we have studied another way of forming an alcohol, and that was nucleophilic substitution. Hydrolysis in the case of a halogen alkane, heating it with sodium hydroxide aqueous would give us alcohol and the sodium salt. Now that was a very good way of forming an alcohol and a specific one at that. What we are about to study further is that we can always go for a reduction reaction. Reduction of an aldehyde will give us a primary alcohol. Reduction of a ketone will give us a secondary alcohol. We're going to study all of this in 18.3. I usually do not explain these at this point because they are well explained in 18.3. This one, at least the one upper. All right. Something we are going to study over here.
Yes,
Right after carboxylic acid, right after alcohols, we're going to study carboxylic acids and esters. During the topic of carboxylic acid, which is about to come on the very next pages, is that we can always go for an acid being reduced by the usage of sodium tetrahydroborate or lithium tetrahydroaluminate, NaBH4, LiAlH4. Among these, what I've already explained back in chapter number 14 is LiAlH4 is a more stronger reducing agent as compared to NaBH4. Also, we always try to use LiAlH4 in dry or non-aqueous conditions. Why? Its reaction with water is explosive. Since it has the capacity to reduce anything, and water loves to get reduced, so the reaction is explosive. So we try to use it in dry conditions or non-aqueous conditions every time, which you're going to see in every step of the book. Remember, we can do the same with the help of hydrogenation, which we used before. The same conditions as alkenes, using nickel as a catalyst and heating. This is something ignored or overlooked by students for this specific reaction, but since mentioned in the book, it has been used in the past paper, comes as a confusion. So make sure you do not overlook this specific reaction. Moving on. Remember, this is something that works as a prerequisite, this one. Why? We already know and we have already studied esters back in IGCSE. Now we know that an ester is actually a combination of alcohol plus carboxylic acid. And what we studied back in IGCSE as well is that if this forms an ester and water in a condensation reaction, this reaction can be reversed. And when reversed, it's known as hydrolysis. Something that we did not study back in IGCSE and we're going to study now in AS is that hydrolysis can be done with an acid and alkali, and the products are slightly different. How? Take a look. When you're doing it with an acid, it's known as acidic hydrolysis, it's mentioned like this over here. It may be simply mentioned like this in a paper. It may be simply mentioned like this in past papers. Don't get confused if something like this is written on past papers. Means the same thing. It still means that we are going to go for acidic hydrolysis. And remember, the word hydrolysis means water being broken down. Apart from the molecule that is reacting with water is also being broken down. So the ester is broken down back into an acid and an alcohol. In this case, we'll get the carboxylic acid and the alcohol, just like the constituent elements or constituent compounds, constituent compounds that we started off with in the first place. Now remember, the alcohol gives the H and the acid gives the OH part to form an ester. And when we hydrolyze it, the water would be divided into H and OH And remember, the OH goes to the acid, the H goes to the alcohol. How can you remember it? Acid always tends to give H portion in usual reactions, hence the name acid. But esterification is the reaction in which acid does not give H. It instead gives OH. Hence we say, in this case, the CO bond breaks instead of the OH one. In most acidic reactions, the OH bond breaks. In esterification, the CO bond breaks. All right? Now, in case of alkali, what happens is that the whole bifurcation would be H and ONA, not OH. So the ONA whole part would go to the acid and the H part would go to the alcohol in the same way. So you get the same alcohol. The only product which is different this time is the sodium salt of the acid. Right? So this one is going to be named as sodium ethanoate. And that's how we name them. Naming is easy because it's the same naming we've done in Esters. OH, talking about in terms of OH. Keep the difference of products in mind. That's what they're emphasizing right now in this case. I hope you get the point. Moving on. Now, the reactions of alcohols. There are many reactions of alcohols as we're going to study. So one by one, starting off with combustion. The combustion is something we did back in IGCSE as well. We do understand alcohols are kind of like the new fuels, clean blue flame, less carbon dioxide given out. The carbon dioxide is reversed because of the photosynthesis way of producing alcohol. So if the alcohols are produced through a potentially renewable source such as crops, fermentation I'm talking about, then it's better, considered good, considered better alternatives to the fossil fuels. So yeah, we mix it with fossil fuels and use it. We sometimes use it by itself by just adding a few additives. Now, when it comes to questions in Cambridge, Cambridge tends to go for the equation. And the most obvious mistake I've seen students making in the balancing of this equation is that they forget that there is an oxygen atom present right there in the structure of alcohol. Now, what you already know in case of tips for balancing the equation is that you always balance the carbon atom first in these kind of equations, especially the hydrocarbon or the organic equations, you tend to balance the carbon atom first. So 2 over here, so a 2 over here. And the total number of hydrogen over here are 6. 6 divided by 2 is equal to 3. So 3 over here. Then the total number of oxygen atoms over here are 4 plus 3 is equal to 7. Don't go for a 7 over here, which he used to do in the combustion of hydrocarbons. But this is alcohol. The combustion reaction is going to be slightly different. I always ask my students, subtract 1 from it, go for 6, divide it by 2. There you go. The number is what you have used over here. That's a very good way of doing it. If you get there is 1 oxygen atom over here, you are always going to end up putting a wrong number before oxygen molecules. And there you go, you ruin the whole chance. And I've seen very good students making the small mistake every time. So keep that in mind specifically. Moving on, substitution to form a halogen alkane. Now this is the exact reversal of what happened before. In the previous reaction, you took a halogen alkane, you reacted it with NaOH, just like we showed on the previous page, and you converted it into an alcohol. Now, if we want to go back, what we do is that we take the alcohol, we react it with HX, whichever halogen alkane we'd like to form, and there you go. Boom, you have the halogen alkane. And it's again a same nucleophilic substitution. It's the nucleophile. Well, the Cl negative is exactly going to be the nucleophile. It would attack the partially positively charged carbon, which is going to leave out of it. And there you go, you have the halogen alkane. So it's a pretty simple nucleophilic substitution, just like we studied previously. How do we do it? In lab, practically, hydrogen chloride gas is used in a dried form, and it's actually made in situ in the reaction vessel. Now, these are the places where you do understand what in situ means and how we prepare some of the reagents, some of the reactants in situ, and we use them. For example, in case of HCl, we do not react it directly with HCl. Instead, we use NaCl and H2SO4 in the vessel. They react right there in the vessel. They produce HCl, and that HCl reacts further with the alcohol. That HCl reacts with the alcohol, and then this part is going to give you the halogenous gain you require. All right. So if I talk about exactly the practical activity, what do? Alcohol is heated in a reflux with a reactant to make the halogen alkane. What were the reactants? We took the sodium salt, we took the dilute or concentrated sulfuric acid. We are going to produce off the halogen alkane, and we're going to collect it as oily droplets in the water over here, which you can see over here. Remember something from a practical approach, you always deliver anything over water which is insoluble in water. Now, halogen alkanes are clearly insoluble in water. That's why we deliver them over water. Now, remember, we have done the same thing with hydrogen gas. We have done the same thing in terms of cracking with alkenes and alkenes. We have been doing it all along because of the same set of reasons, and that is what? That is, they are insoluble in water. Everything you deliver over, underwater, like this kind of delivery, is something that is insoluble in water. Now, in this case, if you go through these lines, you'll understand what you see at the bottom of this. This is the salt. We are going to use the concentrated sulfuric acid. Also, not just the concentrated sulfuric acid, here they tell us that the phosphoric acid, phosphoric 5 acid, H3PO4, can also do the trick, can also produce the HCl. This is the same thing we studied back in the inorganic chemistry portion in the reactions. So yeah, it can produce the HCl, and that HCl which we use in situ. This also gives us the idea about the reactants, the word reactants and the word reagents. Reagents are usually the material we use over here. Reagents may produce anything that is a reactant in situ and that can further react. Like in the upcoming example, substitution reaction with hydrogen bromide using potassium bromide or concentrated sulfuric acid, phosphoric acid would do the trick. Nucleophilic substitution takes place, and we'll get our alcohol, a halogen alkane, my bad. All right. We can do the same trick by going with these different reactions. Now, I can really go with these reactions in detail, but if you closely look at them, we're actually done with these reactions before. How? Let me show you. These are reactions of alcohol, but all of these produce one thing in similar, and that's the halogen alkane. Now, if you go back a few pages, and I'm going to move back a few pages, I'm going to do that to a point that I skip this chapter and go to the previous one, halogen alkanes, and take a look at this. Methods of forming halogen alkanes. This reaction, the same reaction, the same reaction, the same reaction. So really, that page is filled with the same set of reactions, even with all the same conditions. H2SO4, H3PO4, KX or NAX, PCl3, we require heat. PCl5, since it's more reactive than PCl3, can react at room temperature. SOCl2 or thionyl chloride is going to do the same thing. Most of them give us acidic gases in return, apart from the fact that they produce halogen alkanes for us. So it's the same set of the reactions. Good thing is that at one point where it's the reaction, in the other chapter, it's the formation. So there you go. This should be easy. If it's the reactions of alcohols, these are actually the formations of halogen alkanes. So you'll find the same set of reactions with the exact same detail. Nucleophilic substitution is happening. For PCl5, we can do it at room temperature. For PCl3, we require heating, the same set of information. The only thing you're going to find extra in this whole portion is this part. This specific reaction with PCl5 is a test for hydroxyl group. You will see acidic steamy fumes of HCl produced out of it, and this will prove that you have an alcohol at hand. Now, as soon as I say it, I hope you understand that we have previously studied that alcohols can be oxidized using an oxidizing agent, strong oxidizing agent. It can really be acidified potassium manganate 7, or it can be acidified potassium dichromate 6, any of those, and they can give us carboxylic acid. And carboxylic acids have their typical smell, not just so. Carboxylic acid can quickly turn the damp blue litmus papers to red, so they can always be verified in the similar way. So this is the previous test for alcohols that we studied back in IGCSE, and the second test we are studying over here is with PCl5, and acidic steamy fumes of HCl would be produced. Again, they can be tested with a damp blue litmus paper being turned to red. So the confirmation test for both the tests themselves is the same. I am trying to joggle your memory with the prerequisites that we studied back in IGCSE over what we are studying over here from time to time, from reaction to reaction, so that you don't have to open up the book. You can write the hints on your own book. And when you're going through the revision portions from the book, you have both this book content and the emphasized memory or prerequisites from IGCSE at the same place. Yes, Adi, you were about to say something?
Yes. Sir, my grandfather is coming from Pakistan, so I think I need the revision guide. So can you tell me which one to buy?
Okay, let's discuss it right after the class. Okay,
Okay, sir.
so bromo and iodoalkanes, we can always use PBr3 or PI3. Red phosphorus and bromine or iodine are formed with alcohol. Now, students also tend to overlook this line that has been used in past papers. All right. You can't directly use PI3. We use it in situ. How do we do it? Red phosphorus and bromine, PBr3, red phosphorus or iodine, PI3, are warmed with the alcohol. You get your product. All right. Now,
Yes.
moving on. For alcohols, we have this specific reaction. You haven't seen this reaction before. Alkanes, alkenes, or other uh, homologous series, for example, if we talk about halogen alkanes like we did in the previous chapter, you don't see the reaction of any specific metal with them. Starting off with the alcohols, you have this reaction of sodium metal. Now, this is going to be a specific reaction. Previously, in case of hydrogen halides, we have been breaking the CO bond. We have this bond that we have been breaking previously, right? But in this case, since we are reacting it with sodium metal, and metals are very electropositive, we won't be breaking this bond anymore, we'll be breaking this bond. Since we'll be breaking this bond, the entire C2H5O stands, and we simply have O negative Na positive as a product, sodium S oxide. And along with this hydrogen. So the reaction is similar to sodium's reaction with water. Before I move ahead, remember the sodium's reaction with water. If you take a small piece of sodium, you throw it into the water, it moves on the surface of water, becomes smaller and smaller, becomes a ball. If you try to restrict the movement, it shows a permanent flame. If you don't, it would keep giving you the small popping sounds. It would be vigorous and it would be quickly turned into the alkali. A much less vigorous reaction occurs in this case. with alcohol. In both cases, hydrogen gas is given off in the form of effervescence. A basic ionic compound is formed. In the previous case, we were talking about alkali in AOH. In this case, sodium ethoxide ion. Now, this also tells you that sodium ethoxide ion is also basic. With ethanol, if the excess ethanol is allowed to evaporate after the reaction, a white crystalline solid means this whole compound is left. So, if ethanol produces sodium ethoxide, should erase it. If ethanol produces sodium ethoxide, propanol would produce sodium propoxide, butanol sodium butoxide. So sodium alkoxide is the product along with hydrogen. Longer the hydrocarbon chain, less vigorous the reaction is going to be. Not just that, remember it was a basic product formed after this reaction, which we can prove like this. Now you must be thinking, how is that we can see a purple tint or shade over here? That's actually coming from the indicator, phenolphthalein. Remember, phenolphthalein can show you a light pink color in alkaline medium. However, it is colorless in both neutral and acidic mediums. Since we're producing a basic compound, so it is giving you that pink color. All right. The next one is really the esterification reaction, since we have discussed it in such a big detail. Back in IGCSE, no carboxylic acid and alcohols in the presence of a strong ester acid, acid such as concentrated sulfuric acid can give you the ester in water. It's a condensation reaction. Why? Because with the product, along with the product, you get a small stable molecule. You can do it as a practical activity, and it is going to give you a sweet, fruity smell. Remember, this practical activity was present back in IGCSE, and we used to use sodium carbonate to have a layer of ester on the very top of water so that it's easier for us to detect it with its fruity smell, because the smell is not very strong and it faints really quickly. Remember the exercise that we did back in IGCSE about the names and the structures, how we form ethyl ethanoate, the structure, how we form the structure, how we form the name. If I quickly go through that, remember, we always write acid first in terms of its structure, which means something like this. And we write the alcohol, and instead of writing the alcohol like in the similar way, we actually invert it sideways, right? We take the H out of the acid and OH out of the alcohol to form water out of it, and we combine the rest of the structure into an ester. So a chain over here and a chain over here. This is for the structure. 3 simple steps, and you can draw the structure flawlessly every single time. Remember, as far as name is concerned, the alcohol's name is always taken first, and the anol is converted into "-ile", ethanol to ethyl, and the acid part is named after, and the anoic acid, that part of the name, is converted into anoate. If it's not anoic, it's just oic acid, you'll convert it into OAte, which means anoic can be replaced with something bigger, more sophisticated, if not a single bond, maybe a double bond, and hence the name would be converted accordingly. So this gives you the idea how we name or how we structure the esters. Do the exact reverse in case of hydrolysis. In hydrolysis, that's how you break them, and that's how you break water and add H to the alcohol and OH to the acid. You convert the "-ile" into anol and OH into anoic acid to get your names. So this process can be taken forward for esterification or reverse for hydrolysis. acidic hydrolysis. In case of alkaline hydrolysis, you won't get the acid, you'll get the sodium salt of it. We have just studied that part, so keep that in mind. Esters are used in perfumes, flavors, solvents, at many places. We have discussed the hydrolysis of esters, the original product, or the sodium salt. We've already discussed both. All right.
Yes, sir.
Last, dehydration reaction. No, that's not last. I guess we still have reduction. So